Right, now let's look at the link between density and bending strength. Now, in a lot of textbooks, you will see graphs that appear to show a very good correlation between density and bending strength, but these graphs are a little bit misleading. We have to think carefully about what they're showing us. So a common graph that you might see is a plot of density versus the bending strength from small clear specimens. And you'll have points down here for low density species with quite low strength, things like balsa and Polonia. And you'll have at this end dense species with high strength, like some tropical hardwoods. And you'll have things like oak in the middle and spruce about here, implying actually a pretty consistent relationship across species. The problem is that these are plots of averages of those species. The actual variation within a species is quite high. The coefficient of variation for density is typically about 15%. So we would expect for our density about 95% of the pieces to be within, if the coefficient of variation is 15%, we would expect 95% of our pieces to be within plus or minus 30% of the mean value. That's because the coefficient of variation is describing the standard deviation, and 2 standard deviations tells you what you're expecting 95% of the population to lie within. So about 30%, that means, for example, if you have here a density of about 500, that you'll have a mean there, but the density will vary about a third of the way. So you'll expect some density variation, something like that, within the species. For strength, the coefficient of variation is similar, about 15% for small clears. So you would expect a similar variation of about 1/3 for the strength values. So actually, if you were to look at individual specimens within that tested population rather than just the mean, that you will have many points kind of within that rectangle. And that means within a species, you actually have often a very poor correlation between density and strength, even though you see quite a strong correlation across the averages of different species. And that's because of the variation within a species being quite high. So if we were to zoom in and look at the results for one particular species and plot just those on a graph, so density and strength, small clear strength from bending, we would have a relationship that we could describe with a linear regression, but it would be quite a big cloud. And the strength of the correlation between the density and the strength will depend a bit on the species, but there aren't many with a very strong correlation, which is why we don't use density as a good predictor of strength in any real production situation. We're only using density to predict things like compressive strength or fastener holding strength. It's a very bad predictor across all of any individual species of bending strength. And that's just for small clears. It gets even worse if we're looking at full-size structural pieces with defects and slope of grain and so on, because there's a lot more things going on that are influencing the strength. And the variation, the coefficient of variation for a full-size bending test is about double what it is for the small clear. So that correlation between density and strength for full-size structural pieces disappears even more. So why is there a poor correlation between density and strength? In many materials, there is a good correlation between density and strength. The more material you have, the denser it is, the stronger it is, because you have more material. Why doesn't that logic apply for wood? Well, it only goes so far. The higher the density, the more material you have, but it depends on how that material is assembled. And wood is very clever in its construction, and you have variation of the microfibril angle within the middle of the cell wall, which is also very influential for the strength. So depending on the relative amount of lignin and hemicellulose and cellulose that you have and the angle of the microfibril in the wood cell wall, you'll get different values of strength depending on the density, even in a small clear. And within a full structural size, you have knots and slope of grain also coming into the mix. So that's the reason why that you have a very poor correlation usually between density and strength, and why density is very rarely used for predicting strengths like bending strength and tension strength, and is reserved for just predicting things like compression strength.